Okay, uh, good morning or afternoon or night or whenever it is that you're viewing this video. And this video is meant to give you an idea of what a problem should look like when you've attempted it on a homework assignment or problem set or whatever you want to call them. And also give you one more demo problem of for 1D motion. All right. So if you can read this, hopefully you can. If someone would like to have a vertical jump of 1.3 meters, so their feet rise 1.3 meters off the ground, how quickly must they be moving when they leave the ground? Okay, this is pretty standard stuff. And what we want to do in any problem is examine the information that we've been given. And some of that information is given in numbers, right? So the vertical jump should be 1.30 meters. In terms of the quantities that we'll be using in our equations of motion, that is delta x or delta y or whatever you like, right? Because the final position is 1.3 meters off the ground, and the initial position is on the ground, which we'll call 0, the origin of our coordinate system for this problem, okay? So, long-winded way of saying that delta x is 1.30 meters. All right. A couple other things. Let's see. How quickly must they be moving when they leave the ground? So that's going to be the initial velocity of our jumper, right? As soon as they leave the ground, they can no longer push off of it. They're not going to be accelerating anymore. And so, that means that the only thing affecting them will be gravity, the acceleration due to gravity. So initial velocity, that's the thing we're looking for. So we might underline that. And then moving on down, let's see what other information we have. Well, as I said, once they come out of contact with the ground, they can't use their muscles to push off of the ground and accelerate themselves upward. So the only acceleration left over is going to be gravity. And if we go over here and quickly just define a little coordinate system, so up is going to be positive for us and down is going to be negative for us. Acceleration then is going to be negative g. In other words, negative 9.80, 9.81, depending on sort of what average you're using for this, but meters per second squared. Okay, so that's another key quantity. So we have displacement, we want initial velocity, and we have acceleration of this person once they have jumped. And the one last little thing that we need to keep in mind is what their velocity will be when they've reached the highest point, when they've gotten to this 1.3 meters above the ground. Well, at that point, they'll momentarily be at 0 velocity. So V final, sometimes just V, depending on what notation you're using. I'll put the little subscript F in there. Is going to be 0 meters per second. All right? So now we've got all of our known stuff and what we're looking for. All right? And you'll note that some of this stuff isn't explicitly stated in the problem. Right? The acceleration and the final velocity in particular are not stated explicitly, but we can use what we know about physics to figure that out. All right? So we have our known stuff, and now we want to consider the equations of motion for one-dimensional motion, and under constant acceleration, right? Because the acceleration due to gravity of the Earth is more or less constant near the surface of the Earth. Which one of those is going to get us what we want? Okay, well, if we look at the bunch of them, you will find, well, we could think about this one, right? We might think of this one right away because it involves the thing that we want to find. All right, there it is. But we run into problems as soon as we start thinking about how we might actually solve this, right? We know acceleration, we know delta x, but we don't know time. And although we probably could go away and find time, like how long it takes for this person to rise from the ground to the top of their trajectory, to that maximum height, well, let's see if we can avoid that. If we look at another equation of motion, we might find something that is more promising. So V final squared equals this 2 acceleration delta x. Okay, now this one looks quite promising, right? Because it involves the thing that we want. It involves things that we know and nothing else. Okay, so this is the shortest route to success in this problem. So let's move this over here. We start with this equation. We can start substituting in some quantities right away, or we can solve it for the initial velocity. I don't really care which. I'm going to solve for initial velocity first, just so you can see how that's done. So all we need to do is take the this second term here on the right and subtract it from both sides. And then we need to take the square root of both sides. So the square root of that, and the square root of this, and that'll give us v0. Okay. Now, when we substitute in, well, the first term's just going to go to 0, right? That's that initial, or rather the final velocity right at the top. So that goes to 0. This acceleration is going to be negative g. So don't drop any negative signs here. So 9.8 meters per second squared. And the last thing is going to be delta x. That's our 1.3 meters. And this whole thing has to be square rooted. Pardon my poor writing. Okay, and that will equal our initial velocity, which we know is going to be upward, right? Because we can look at the physical situation and say, yep, they're jumping up. So if we look under here, it's good that we didn't drop any minus signs, because otherwise we'd end up with a negative under a radical, and we all know that that usually ends in tears in physics. So these two negative signs will cancel each other out. We've got a positive number here because we're going up 1.3 meters, so up is positive for our displacement. And if we multiply all those things together and then take the square root, so let me just 2 times 1.3 equals, and then we can take the square root of that thing, and we find that the initial upward velocity of this person must be just a hair over 5 meters per second. We've got 3 significant figures in the given quantities in the problem, so I'll keep 3 significant figures here, and that gives us 5.05 meters per second. And just to be extra special clear, I'll say upward. I'll circle that. Okay, so there's a demo problem, and there is also a nice layout of how you might attempt a problem, right? Show that initial equation that you settle on is the good tool for the problem. Definitely identify the relevant quantities you're going to be using. Usually a good idea to define a coordinate system as well. And then show a couple of steps of your work. Box, circle, underline, highlight, whatever it is your answer might be, and you're done. Now, of course, I think, kind of did this live, but I think this is correct. I don't think I punched anything into the calculator wrong or made any obvious errors here, okay? But even if it wasn't, right, if I had made an error, right, I had gotten a negative sign here or something like that, remember these homework questions are graded for completion, right? This is me encouraging you to engage with the physics, really learn your stuff, and I don't want the pressure of being correct to be there. In fact, the plan is for me to actually give you the numerical right answers to all these problems before you turn them in, so that you can check your work at least against that, and I'll release some complete solutions afterwards. All right, so we're getting up towards 10 minutes on this video. I think that's enough talking from me. Hope you found it useful, and I will see you later.